So we can immediately generalize this to all norms, LP norms. So an LP norm is just the penalty on the regression coefficients that penalizes the P norm. And just to refresh your memory, the P norm of a vector is equal to the sum of the entries raised to the pth power, and that sum then raised to the 1 over pth power for P equal to a value between 0 and infinity. So when we do LP regression, we're simply adding the pth norm, the pth norm raised to the pth power. So we have our goodness of fit term. Again, it's the squared error of the sum of the squared errors using a linear regression. And then we add lambda times the pth norm raised to the pth power. Lasso we saw corresponded to L1 regression, where P equals 1. Ridge regression corresponded to L2 regression, where P equals 2. But now we've generalized this to where P can be any value from 0 to infinity. And so if we look at the level sets of the penalty, so this is how the penalty looks. This is not the goodness of fit term, but just from the perspective of the LP norm penalty on the coefficients in a two-dimensional problem, we get something that looks like this. So when P gets larger, we get penalties that look more square. When P is equal to 2, then we would penalize all vectors W along a circle equally. So any solution W that falls along this circle is going to pay the same price according to the penalty term. When P is equal to 1, we get this diamond. So the L1 norm of any vector along this diamond is equal to any other vector along that diamond. Then as P shrinks between 1 and 0, it shrinks from 1 to 0, we then get this sort of an inverted penalty, where it then starts shrinking to the point where in the infinite limit as P equals 0, we simply pay a penalty. We pay a price if it's non-zero or not. And so that's summarized here. The infinity penalty, so the L infinity norm, simply penalizes the max value of W. So it'll just simply say minimize the maximum value of W. As the penalty is greater than 2, the norm is going to focus on large entries. When it's 2, again, large entries are expensive, and it encourages smaller size entries. When we start to get to P equals to 1, we get into the realm of sparsity. So P equals 1 encourages sparse solutions. And then as P shrinks below 1, it also encourages solutions, but now we've lost the convexity of the set of points under a certain value norm. So all points that are less than this norm are within a convex set, meaning that there's a line of sight between any 2 points. But now once we shrink the penalty to below 1, any vector that satisfies a LP 1/2 norm less than this value is not in a convex set. So for example, this point and this point don't have a line of sight. And so the ramifications for that, I'm not going to discuss convex analysis in this class, but the ramifications for that are straightforward. And they come in our discussion of the solution of these problems. So if we look at the solutions of the LP minimization problem, again, the solution for L2 is the ridge regression solution. We've already discussed that. It has a closed form solution. When P is greater than or equal to 1 and not equal to 2, we can solve it by something called convex optimization. So again, we won't discuss convex optimization in detail in this course. It's usually taught in its own course. But 2 facts about this are very important. So first, there are no local optimal solutions. So again, if we try to minimize this over W for a P norm where P is greater than or equal to 1, then we can use an algorithm to find, then there's one solution to that problem, one local optimal solution, which corresponds to the global optimal solution, and we can find it using an iterative algorithm. And so that's very important. When P is greater than or equal to 1 and not equal to 2, we can use an iterative algorithm to find the global optimal solution, guaranteed. But when P falls below 1, so when P is between 0 and 1, the problem is no longer a convex optimization problem. And what this means is that we can again use iterative algorithms to try to find a minimum of the objective function. But in this case, we can only find a local minimum because the objective intuitively looks something like this. So depending on where we start, we might only find a local optimal solution when P is less than 1. But when P is greater than or equal to 1, the objective looks something like this, and we can use an iterative algorithm to find the global optimal. So to sum up LP, regularized linear regression, we've seen that we've discussed 3 techniques now that can be formulated as optimization problems. We've discussed least squares, where we had a goodness of fit term equal to the sum of squared errors, and we've had no penalty. And we saw that an analytic solution to this problem exists only if X transpose X is invertible. We discussed regression, which has the same goodness of fit term and a squared norm penalty. And we saw how we can solve this, the minimum for W, analytically in all cases, as long as our regularization parameter lambda is greater than 0. And then in this lecture, we discussed the Lasso, the L1 minimization problem, where we again solve a goodness of fit term, which is the sum of squared errors. But now we penalize the L1 norm of the vector W. And we didn't discuss an algorithm for this, but we did discuss how we can find the global solution to this problem using an iterative algorithm derived from convex optimization.